Hi there. So this video, let's do a review of what we have done now with XFLR5. But reminder that at the end, we want to design the wing, but that wing needs to generate the required lift. Okay, that is the most important requirement. Then we have these requirements that we want to do things in an efficient way, meaning low drag, total drag, that you can split then induced drag, and you have also low viscous drag. Okay, so the one that it from an aerodynamic point of view that we can that we can control is induced drag. So that is the idea, the idea designing also the wing, that you want a lift distribution as close as possible as the elliptical one, because we have seen from the theoretical results but also numerical and practice that the elliptical one gives you the minimum induced drag. But getting that elliptical lift distribution is not quite easy. Now, so here I show you a few wings, and see that we have now the red line. This one represents the ideal elliptical distribution, and then we have rectangular wing, which is this green line. Okay, then we have two different tapered wings, and see that according to the taper ratio the distribution change. Okay, so the one that probably gets closer is the orange one that have a taper ratio of about 0.331, and see that it gets very close towards the tip in the outward part of the wing, but then in the inner part it's a little bit different. Instead, the one with the taper ratio of 0.6 is very close in the inner part, but in the outlet part it's not very good. Instead, the rectangular is quite different. So remember that the induced drag is related to the thick vortex, and that we have it in this trend. So so it's natural to think that we want to approximate the elliptical lift distribution, but it is enough to do it just in the outward part. So probably you manage to get something about 20% of that distribution close to the elliptical one. It is already a good job. It's very tricky to get it also in the inner part. You will need to start to play with the core length and twist angle, and probably adding aerodynamic twist. So it can be very tricky. And also maybe you will realize those two things. The only way that you will approximate complete these elliptical distributions by getting an elliptical wing platform. Okay, you will need in XFLR5 you will need to have different sections to control that, or by adding washin in the internal part and washout. So you add a little bit washin and you control that one, and adding washin is not recommended. So remember that designing the wing, you need the required lift close to zero degrees. Okay, it's in optimal condition, and also probably just the outward part, like 20 or 40% of the outward parts that is following that elliptical lift distribution is good enough. And also reminder that we need to control also the stall characteristic of that wing. So for instance, here we have, in this one, we have two wings, same taper ratio, but see that when you have a taper ratio below 0.6, the wing starts to become now very loaded in the tips. Okay, so this means that it will stall first. Okay, so here, attention, we're looking at the lift coefficient. So to control this one, what we do is just reduce the angle of attack at the tip. Okay, and now we're in a good design condition. So see that it's not stalling anymore here. Now in the inner part, of course, we're affecting the lift curve slope and everything. So probably we'll need to change the incidence angle or the angle of attack to get the right lift. But these are variations that are very small. We're talking about 1 degree, half a degree. Okay, it's not things that you will see 5 degrees. It's very small variations. Okay, so these are the basic tips now to design your wing. So that being said, let me launch here the program. I will open a file that I already created the wings there just to review. So let me go here. We have different wing platform. Okay, so already run several cases. So I just want to show you, for instance, let's say that, let's start with the classic rectangular wing. Okay, so remember that always you go here in each of these, here in graphic you can change how you visualize everything. I like to use this. This is okay, 5 views. So if you right click, you can change what you see. So let's do this one. Let me put here define graph, and let me go CL CD. Okay, this is the polar. Okay, we have the polar for this one. Let me save. So here you see that we have alpha and we have the force. We don't have lift. Interesting, the force. And let's suppose make this assumption that our target is 4,000 newtons. Okay, for lift. So see that in this condition we need to be about 0.8 degrees. Okay, so see also that we have this particular now the lift curve is low. Remember, by default it's computed in 0, 0, 0. Okay. So it's here, then here you will have the center of pressure, aerodynamic center, everything that you have defined here. Okay, you will find all those values there. So it's always a good idea to look at this one, but this one strongly depends now, and the story depends in the airfoil shows, and I will show you later how this will change with another airfoil. LD, also remember that we want the maximum as close as possible to our cruise condition. Here we're saying that it's something about 0.8 degrees, and see that here probably is not there, but it's close. It's different of 1 degree, it's not that bad. Okay, and well, let's see what we have here. See here, probably we can do another plot. I don't know what comes to my mind. Okay, let's do the classical here. You go current graph it, define graph it, and let me go alpha CD viscous. Okay, so here with the CD viscous we can take a look at the only the viscous parts, and we can see we have this drag bucket. Here we're using a 2412. Okay, so we shouldn't have that. This effect is just the three-dimensional wind and the interpolation that. So this is it, how you do it. And to remind you that, for instance, you want to create a new wing or a new airplane, you have it here, define new plane, and we're just focused here in only the wing. So disable everything, but here you can design your whole stuff. If you want to add the body, you'll have it there. I'm not going into details that. You have the new wing, and then define and just set up the wing. So let me enter here. Okay, no, I don't want to save. And to show you what I have in this rectangular wing. Okay, so if you go to edit wing, so see that I designed a very simple wing. So all the wings that I designed here, we have the same semi-span, 0510 will be the span, and we're using this airfoil. So remember that the airfoil, when run with the LLT, we need to run for all the Reynolds numbers that the wing is going to see. So here already know this is a constant core, so it's quite easy. You run that one. So a good idea to get the upper and lower value, above the one that you have with that, and you do an increment of 100,000. So if the value is 3 million, do 3.1 and 2.9 million. Okay, just to get a good interpolation. So see that we have no twist, nothing. Okay, so what we're interested, we have the performance of this one. We go here, and let's say that I want to visualize for 1 degree, and here you have. Remember that you can always go graph, plot everything. You have all the plots. So let me put it here. Okay, to have all the plots, you press R and use fit to screen. Okay, let me go here, and this is the one that we're interested. Or probably better we go. If I press 4, I have it here. And remember to see this the elliptical curve. Right click, show target. And you put here max local CL and select this one, and you will have that reference curve there. Okay, so you have different ways, different curve. Okay, you can put like this. Okay, it's up to you. So at this point I'm using this this one here, this one max local CL, just to have it starting from that point. So see that the problem with this rectangular one that is producing too much here. Okay, so what we can do to control this in the rectangular wing, we can go and add a little bit twist to reduce that one. So that is what we have in the second one that I have here, twist. So I open here again and edit this the wing here. See that you have the values, and just add a twist from 1 to -1. Okay, and if we plot this one for 1C, okay, why? Okay, enable here, and now I can see the value. See that now is a quite good, okay, win. So if we compare this one with the other one, see that we're producing too much towards the tips. Okay, here now, this one, by adding that twist. And this is already okay. This is towards the tip, as I mentioned, that you want here the elliptical, close to elliptical lift distribution, just to reduce intensity there. Okay, so also probably would be better here to use the maximum wind CL. Okay, and we can compare with this one here. So see here that we have excess here. You change a little bit the twist, and see that now you control. So this is already a pretty good distribution. And the next case, this is the twist 2, just to show you. I go here and we go into the wind and see that I added a new section at 2.5 now by looking at the previous case. And let me go back here. So kind of in 2.5, see that I'm below. This is probably the largest difference. So let's see how we can control that. So what I did here was that another section there, and look at that, now I'm controlling the progression of twists like this, from 1 to 0.5, and then from 0.5 to 1. So this is a gentle twist here, geometric twist, and then I have kind of a larger twist here going to a negative value. We can reach maybe this same effect adding aerodynamic twist, so you will need to add the new airfoil, and that's all. So if I plot this result now at 1, need to visualize here 1, see that is a very, very good approximation of elliptical curve. So this is what we want at the end of the day, something close. It's very difficult to get it in the internal part now, and this is one case, as you see this slides, that the rectangular wind is the only one that you can get this kind of results. Okay, when you have taper, it's very difficult to have it. Okay. So for instance, this one is the only one that you can have the elliptical one in lift, but also you can have it when it comes to the coefficient. So see that the coefficient also can get that elliptical behavior, and the circulation also. So the recirculation is related to lift. Now, so you look at the Kutajakonski theorem, see that it's related. So see that if lift is already elliptical, circulation will be as well. And what is interesting is also that in this plot you have also the induced angle. Okay, so remember that this is basically at the end of the day that what we want to do. As you recall from the theory, elliptical wind, the induced angle, the downwash, okay, it is constant. And see that here kind of is constant. You have these jumps due to the changes that we have added, but see that it's very constant. And then in the tip here is that we goes large, and this is the one that is responsible enough for that tip. So this is what we want to minimize. So if we compare all these, let me go the twist one, see that what happened here. So see that the intensity here is at 1.6, and here by adding this one, okay, it's about the same, a little bit smaller, but we have better control here. But if we compare with the base wind, see that the rectangular wind, it generates, the one with nothing, it generates a very large thick vortices. We have a very large induced angle. Okay, so it's about 0.4 in the inner part and 2.2 in the outer, so it's very large. So see here that even this one is larger in the inner part, but not that much, but then it's much slower here, and then the other ones is that we keep it constant. So you might wonder why, okay, this wind they have a problem now, because most of the time you're going to see that this rectangular platform is used a lot in especially in general aviation aircraft, like this example that we did in Cherokee Piper, and they don't add any twist, nothing. So you might wonder why that kind of wind is widely used, and the reason is that it's very easy to manufacture. You don't need to add any twist, anything. Very easy to manufacture. Okay, it's just that. So sometimes the final decision is also not only based on the aerodynamic performance. You will have also other factors that can influence the final decision. Okay, so see that this is the airplane, and you have here the characteristic, no twist, just the incidence angle at the tip. Okay, so maybe you can say that the original one is not good, and you go for this one and you get a better behavior. So now let's do the exactly same wind, and we add taper ratio. So will be this case, and let me show you. Well, here I can show you. So this is the wind. Let me hide all this here. Okay, well, it's this one. See that we're adding some taper. The taper is 0.4. That the value, recall also that this is a theoretical result, and we have some plot here that the ideal value is something there, okay, 0.4, 0.3, probably 0.5, okay, to get the minimum induced factor. So this is all. We have the same win, and the base one, no twist at all. Before showing you the results, let me do the comparison here of these three rectangulars. So see that we are targeting for 4,000, so see different widths, different values. We have something, and this one that we are added the twist at the root. See that this one now we require a lower value to reach that quantity, and obviously if we compare now the polars, you will see different behavior. So for the same leaf, okay, so here we have a crossover point, okay, meaning that here this one starts to, for the same leaf, so you go here, for instance 0.24 for this leaf, the gray one produce less, see the total. Then also you can do that subdivision using the induced drag. So here in viscous you can check also for 1 degree the gray one produce less, or we can visualize also here the let me go here, define graphic instead of the viscous, the induced drag. Okay, so actually see that actually the gray one in this case for a given angle of attack producing a little bit more induced drag than the other, okay, but remember that produce more leaf, so it is a compromise between everything. So for an angle of 1, this one is producing more leaf, so it is expected that the induced drag will be larger. Okay, so it's always a balance. So, but from the theoretical result for the distribution, the gray one is the one that should produce the smallest thick vortex. So now let's take a look at the new win and the taper. So if I go here, edit win, see that we just modify this. I added my taper ratio, I added this value, the offset. This is mainly visual, okay? The LLT method, probably the nonlinear method implemented here, will see some effect. But generally speaking, the LLT method, without any of those specific corrections, this swept angle won't have any large effect. No twist, the standard airfoil, and you just run the simulation. But now it's interesting, go into taper when you define your analysis. And by the way, we're running all these cases for a same velocity, okay? So this is a condition that we know the velocity. In the next video we'll show you that sometimes it might happen that you know the velocity, you have just, you know, the weight, approximation of weight, whatever, and now you want to get that velocity. So you can get an idea that you can do many analysis at 30, 40, 50, 60 and construct all these polars. But there is another command that you can do, a batch analysis, that you will see here. For instance, you fix the angle of attack, and then here you will change velocity. So we'll show you that, and you can construct everything in function. Now it's velocity. Okay, now velocity is constant. See that it's telling you that you have all these Reynolds numbers. So you have to be sure when you generate your win that you need to cover everything. Okay, so see that I have already my Reynolds, so that you can do a batch analysis here, and you need to construct this table. Okay, it's done manually. Honestly, I don't see how to do it automatically. If you find a way, please let me know. But one thing, that when you do it once, this stays safe. So if I later close this program, I will get the same table. Most of the time you need to have all this Reynolds, so you can do it manually from, I don't know, from 500,000 to 10 million, and you're going to have all the table there. To run in parallels like this, so in my case I have 12 threads, and it shows here 6, and there is no problem here. So you go analyze, and you will run everything. I'm not clicking there because I already have my Reynolds. And you go to the win design, and you do your taper win. So see that now I put it here, and let's see the results. So one thing that also I want to point out here, that I mentioned, that the win tends to inherit all the properties of the airfoil. So if you check your 2D airfoil, you will see that the point that when it's you get the angle of attack for zero lift is something about here. So see that they are all centered here. This one is a little bit different. Remember that we changed the twist and everything, so you have that shifting. But clearly you see here that it's inheriting a lot of information. But see that taper also have an effect that will reduce, you know, your curve lift slope. Since that might be evident, you have different surfaces. You know, that effect you will see it here. So now in this case, you want to force your target 4,000 newtons. See that now you need to go a little bit higher, 1.8. Remind you that here we don't have any incidence or setting angle at the root, so you put a setting angle there, things will get better. But we can check here, for instance, you go now and look at this is a red curve. So for a given lift coefficient, now this one is producing less induced drag than the other curves. Okay, so now you can look at these plots in that way. Also, you can see here that for a given alpha, this one, the red one, is always the best one that you have there. Also see that in the LD, we have a good effect there. So see that by simply adding the taper and that conceptual result, that theoretical results, we improve a lot since without doing a strange things. And now if we go to this distribution, span-wise distribution, and let's go to 1, see what we have. Okay, so let me go the base rectangular, which is this one. Okay, you have the distribution here, local lift. This is, and if I go to the taper, see that what we have is very damn close to the elliptical one, just by adding taper, no twist, nothing. The only thing that we have here now is you look at the CL, is that maybe where the stall is very close to the tips of the wing, so probably we can add a small twist and shift this in bore to avoid that problem. But if I go here 4, 5, 4, perfect. See that this is very close. This is already a very good solution. We can, okay, improve it a little bit. Okay, so how to improve that one? The first thing is that we can add the twist to avoid the problem, this problem, CL. See that here will have the tendency to stall first. So as you go, you add that new twist. So let me show you the geometry here. See that I didn't do anything, but just the twist, 1 degree. Okay, 1 degree, and I plot my results for 1. Graph everything. Okay, and let me put here. Okay, I need to show also. See that now we have this. Okay, and look at first the CL. Okay, so now let me go individual CL. See that now we shifted. Now it's not installed at first here, it's something more inboard. As we look at here, a local lift, it's still good. See, remember that it's very difficult, as I mentioned, that to get it elliptical, unless you get an elliptical platform or you work for using the rectangular platform. This is very tricky to get it very close to elliptical. And since it gets worse when you go high speed, that you have this setback angle. Things get even worse. So we're just focused that we want towards the tip. So probably 20% of the span, is you manage to get it elliptical, is enough. Okay, so our semi-span here is 5, so as you get 1 meter close, I think it will be a very good result. Okay, you are reducing the intensity. But see that this is the idea. Here, see that it's very good results. Okay, very close to the elliptical. So this can be controlled, okay, by adding twists. You also, one result when you start to play with the twist, you will realize, see that here you are not producing enough lift, so you will have, you will be tempted to increase the angle of attack. So as you increase the angle of attack, that is washing, it's not recommended, but as you increase angle of attack, you will get closer here, and here you will be to decrease. So it will be an strange wind, no? So down wash here, then wash in here, and then you go wash out. The other solution is changing the wing core. So you can change the wing core, so you increase here a little bit, and decrease a little bit. But you see, when you start to do those modifications, you will be approximating an elliptical wind. So let's stay away from that one. So if you want to add sections, like for instance, a section and 3 and 1, it's just to control the twist angle. And the idea is just to get it as close as possible in the outward part of your span. And if we check And okay, so let me go to the polars. Okay, so if we go to the polars here, and let me fix the screen, everything. This is what we have. Okay, so let me change the color of this one. Okay, to avoid confusion. So let me use this one. So see that now the new one, this is what we have. Okay, so it's a much better result, okay, than the red one with washout the base ones. So in this case for 4000, see that we improve it a lot by adding that twist. So now about 1 degree, this is a very good cruise condition, okay, and close to this one. And see that very small differences in angle of attack are required, like 0.5, 0.8 to reach those conditions, okay. It's strange when you need to do something from 0 to 3, it's very strange. And this is what we have. Also see that there is an effect in the moment, changing the slope, okay, but this is later we're going to see a very strong difference when I show you a new airfoil. And this is okay, this is already a good design win, okay. This is something that you can use, you can propose, okay. And if we look here in this drag, okay, so see that in this specific win, now this new taper win that we're proposing for the same angle of attack, let's say 1 degree, produce more lift, more induced drag than the standard one, but this is clear because for 1 degree this one produces more lift. More lift means more induced drag, okay. So you should look at here in this polar for the lift coefficient. So see that it produces a little bit more because we're producing more lift, but see that it produce less induced drag than the others, okay. Then you have here this crossover point, okay, where the performance get worse, okay. But these are usually our operating conditions will be somewhere here. And the final one is that one, this one that we added more twists, a second twist, okay, a new section to control motion. So see that here, the effect now, okay, since get water a bit better in terms of the trim condition for the lift. So at 4000, see that now we're at 0.8, close to the rectangular ones. Okay, so you see here the progression. So by adding that twist, we're shifting here, but getting better in lift. Still, we're producing more induced drag because we're producing more lift. Okay, but if you look at here, it is okay. So what we did in this case is was very simple. Edit win, and now a new section. So see that I added a new section. I didn't change the core, okay, I kept the same linear progression in core. I just changed this angle. So see that a very gentle twisting from 1 degree to 0.9, and then here I went aggressive to 0 to control all the characteristics. And if I look here, let's see what we have. 1 degree, okay, perfect. See that this is a very good distribution that we have here. Okay, still it might be, you might think it can be better, probably adding another section, some control there, but this is already a good result. Okay, so this is what you need to do for the wind design. Then let's plot everything. Look at the induced angle also. So we reduce it here, low angle, then at the tips it's not large, and you can control with the other one. So remember this induced angle, the downwash, the one that at the tips, you want to reduce it because this is directly related to the intensity of that wind tip vortex, and that it will produce that, increase that induced drag. So see in this case, it's very large, that induced drag here. In this, see that we reduces a lot. Okay, so this is it. This is how you do it. And just to show you the new airfoil, and to remind you how to read an airfoil. So the airfoil to read, the airfoils that you need to read here is exactly the same format as the one used in Airfoil. Okay, so every airfoil that we use in Airfoil, you can read it, but it has to be exactly the same format. So you should, let me say in my case, I have the airfoils here. So you open one of these, you will see that it's exactly the same format of an airfoil. So to read that airfoil, you go here, open, look at the folder where you have the airfoil, and I will read this airfoil. And that's it. You go to airfoil direct analysis, airfoil direct analysis, and you have your airfoil there. So here, this is the airfoil. So we have the model also direct foil design that you can look at the airfoil that you have there in buffers, also that, and You can hide as well, do not show. And here also it's very handy now this model because you can also change points. Okay, it's like the GDS model in Airfoil. Okay, I don't recommend you to do that, but okay, direct foil analysis. Let's go here, Airfoil direct analysis, and let's run for this airfoil. Okay, at the Reynolds number. So you will see that here, batch analysis, you have already the table. So we want to run for this airfoil, analyze, and let's get all the polars. So see that it's running every Reynolds number for all this alpha, and is populating the table here, a lot of results. I'm using 6 cores, okay, so it's running parallel, it's quite fast. I will save. Okay, it's always a good idea to save. And now see that you have all your Reynolds, see that there are different behaviors, okay, both airfoils, but let me go back to win design and let me show you, for instance, let me pick up one win. I will take the rectangular one, so I will hide everything. And I will change the rectangular one. So see that I will duplicate this case. I will call it new win. Give it a name. Edit, and you can edit the whole definition, and then you go into the win. Okay. And rig the new airfoil, that's all. And actually you can use aerodynamic twist, different airfoil. So we put this in, and I just put there the new airfoil, and I'm ready to run. Save. And let me run this case. Before running, define the analysis, define analysis. So you can do right click or analysis, define analysis. Okay, so we have fixed velocity. Later I will show you the other options. Remember also that here you can change aerodynamical data, density, viscosity. You can give inertia, choose the type of analysis for your moment where focus is LT. Will also show a little bit the vortex lattice. That's all. So let me press save, and we're ready to run here. So usually will run in these angles. Okay, it's the linear regime for the wind. We're not interested in the stall, that stuff. Analyze, and this is it. We have some results here. Okay, but I'm interested in going here, and what I want to show you in this case. Okay, it is new wind. Okay, rectangular wind. So your rectangular wind and the new one. So we are using a different airfoil, and I don't see the effect here, or probably what happened. So this airfoil, it has a very low moment, so it doesn't have that strong effect here. It can be classified as let me go back here. Probably this is, so look at the moment. It is a self-stabilizing airfoil. So see here that the moment can go positive but very close to 0, but for some reason here it gave me this one. Probably shows, but this is an interesting characteristic of this airfoil. Okay, it's a self-stabilizing, and if you use this very specific airfoil, you will see the specific behavior here, that the moment is changing probably for this kind of wind that we're using. Doesn't have an effect. So let me go and see if the taper wind, we see that clear effect. So duplicate, I call it duplicate, give it whatever name I want, and I want to edit that one, and the only thing that I need to change here, it is this. Okay, so new perfect, yeah, I think it's the taper one should work. Should have a different result. Define analysis, this is okay. Analyze. So we have the taper and the base taper, and this is what we have. Okay, so yeah, it didn't have a very strong effect. Probably shows the wrong file, but just I show you how to read a new airfoil. Put it there, duplicate the case, and very easy. Then you can change the parameters. For instance, you see that airfoil that here, kind of here you can see this is a drag bucket here, and you see we have the influence here. So then also remember that you can visualize like this using the LLT. You pick up an angle, and then you can select now this option, but this is just visual now. This is by no means is direct representation, nothing. Okay, so you can do it as well there. Then also the other thing that before ending that I want to show you is you go here, analysis. Okay, you can define analysis. Okay, give it a new name. Okay, well, I don't need it. We'll put it automatic, and you can choose a new method. Okay, so the LLT is this quite simple theory. Okay, it's a nonlinear LLT that takes all the data from the airfoil and then superimpose a single bound vortex and add the effect of the downwash. Then we have the vortex static method. Okay, so it is a panel, kind of a panel method, but it takes only the curvatures, the cambering effects, and this one is the whole surface. So I recommend you also the vortex static methods. They are very efficient, but I don't recommend you to use it in viscous mode. Okay, this is a correction added. All these methods are in basic, so the viscous is a correction that honestly I think it doesn't work very well, at least here in XFLR5. So disable this one, and you are ready to run also using the vortex lattice. So in vortex lattice, you don't need to run the polars. You only need to define the airfoil. And just to show you, when you define the airfoil, the solver automatically computes the camber line. See that this is the airfoil camber line, and then it will put this panel there, and it will compute your circulation and then get the lift. And this is what we have. Okay, you have a delta P here, a difference, and then you can have your polar. Okay, so our new result here, and let's see what color it should be. This here, let me change color here, so I put it white. Well, white is not very visible. This one. Okay, we have it there. So see that new method. The difference here is obvious. Remember here we don't have the viscous component. So you can see here that this is a correction. It's a CD0. Recall for the equations, the polar. So you just can shift this one by a CD0, and very often we know that value. Okay, you know your clean wind have a CD0 that you computed when CL is 0. So CL0, you know that the drag, everything is the skin friction drag. So you compute it as CL0, shift this curve, and you are done. Yeah, and very similar results. Okay, so that's all for this review. Next video will show you how to use the other options, the analysis, how to run some other type of analysis and define lift. So thank you for your attention, and see you next time. Bye.